that comes out of these, let's say, these 4 emissions. Say, oh, one line here, one line at this energy, one line at this energy, this, and we say that is only one atom, one element can produce those lines. So we can identify the element, the trace element in, let's say, our glass sample or whatever sample we have. Here's what it would look like. Here we took something that looks like it had a lot of metal in it. We shone light into it, and what came out were all these bands. This band means it emitted light right around this energy level. It was in kilo electron volts. Never mind the units here. The point is these are energy levels. So it produced, it emitted at this energy level. That only potassium will emit there. We see titanium also. There was some titanium in this sample. Copper and nickel, even some gold there for some reason, and lead. So this sample had a lot of metals, and we can see it. We can see it by shining light into it, and we see where those emission lines were. This emission lines were only for copper. We know there was copper in there. This is only for molybdenum. This is only for zirconium. This is one way of analyzing of the elements found in a sample, the trace elements found in a sample. Other ways of exciting the samples are not with light. They're with electricity or even heat. The carbon arc emission, that's done with electricity. You put a voltage between carbon electrons, put your sample in between them, you put a high current in them, you'll excite the electrons, and you're going to see what light is emitted. And by the light that's emitted, we know what the element is. Or even if there are several elements, we know exactly what those several elements are. Here's another interesting one, the inductively coupled plasma emission spectrometry, ICP. What happens is you take your argon, you put it, give it an electric charge, a very high electric charge, and you'll create an argon plasma. That means the gas has a single charge. Now, if let's say the gas has a negative charge, you'd assume that everything repels everything and it'll blow up. But you can keep this contained in a magnetic field. The way magnetic fields, the way they react with electric charges, it can actually keep this argon plasma, even though it really wants to blow up, you can keep it confined. And, you got a lot of energy in there. It wants to blow up, and it's confined. And all that energy is heat, becomes heat. It gets superheated, in other words, to incredibly high temperatures, 7,000 to 10,000 degrees Celsius. This excites the electrons. You put the sample, usually in aerosol form, because I don't know what else can survive this. You spray it in there, you shoot it in there, it'll excite, I'm sure it'll be vaporized by then, but anyway, the atoms in there will get their electrons excited, and you can again look from the spectrum as they emit light. You can see what the different elements that are emitting at different wavelengths, at different frequencies. You can see what they are and see all the elements inside this sample. Now, just a curiosity, 10,000 degrees Celsius. That's about 5 times the temperature of the sun, and you can argue it's 20 times what they call the physical purgatory. Now you might think that they don't know the temperature of the purgatory, but they did actually relate the temperature of the purgatory, and this is 20 times that amount. How I know that? Well, let's get back to our subject here. There's another way to analyze elements, a very good way, if you can get it. That has to do with nuclear activity. The nucleus of every atom is composed of protons and neutrons, and we can assume they're stable. You can shoot neutrons into these nuclei. When you do, they can get absorbed into the nucleus, but then the nucleus got to rearrange itself to accommodate these extra neutrons. When the nucleus rearranges itself to accommodate it, again, there's energies involved. Energy is emitted in the form of gamma rays. Every element has a different kind of rearrangement. Every element has a different kind of gamma ray discharge. You can identify the element based on the frequency, the wavelength of this gamma ray that it produces after hitting it with neutrons. 2 things about it: it's very sensitive, very precise. You can certainly identify them very easily this way. Also, it's non-destructive because neutrons don't do much to the sample. So it's a very useful way to do it. Problem is, it's expensive, and you've got to find a way to send these neutrons, shoot them into your sample. You're going to need a nuclear reactor or some kind of particle accelerator in order to do that. So it's not commonly done, but It certainly can be, and if it is, you have a very good way of finding the trace elements of your sample. Briefly, talking a little about nuclear forensics. This is when people want to steal nuclear bombs. I know it's not generally a crime, but it's done, and maybe we'll talk a little bit about it. Well, where do these criminal elements, or I don't know if you want to call them criminal elements or political elements, whatever you want to call them, where they're trying to get nuclear bombs, where do they get them from? Now, they have to get their fuel. They have to get the uranium or whatever they fuel their nuclear bombs with. So where do they get that from? Well, the obvious place to mine it, or to have another country mine it and buy it. This is what Iran is doing. They claim it's not for criminal activity. It's not for violence. It's just for peace. But come on, this is nuclear waste, and this is nuclear. This is nuclear fuel, and we're talking about the Middle East. Anyway, getting back to where we were. That's, sort of legal to buy it from places that are mining it, but very often it can certainly be stolen from refinable nuclear waste. Now, every nuclear power plant produces nuclear waste, and this nuclear waste you can refine it and get your fuel that way. In fact, it's easier. You got a lot of nuclear fuel in the nuclear waste. The problem is you got to refine it, and it's not easy to refine. And right now, it's cheaper to actually mine it and get the mine stuff than to process the nuclear waste, even though you can process it and turn it into nuclear fuel. So right now, they're just being kept on site. We really don't know what to do with all the nuclear waste, but right now, it's not so much of a problem. We're just keeping it on site. It's generally not guarded because you get too close to it, it'll kill you. We don't really have to guard it. It'll pretty much guard itself. Anyone gets too close or tries to steal it and put it on a truck, they're not going to live out the week. So people generally don't steal it. Now, but again, it certainly is useful as a nuclear fuel. They're taking this waste, which is not very well guarded. So it can be used. But again, it kills whoever tries to steal it. Now that we've had, the world has had some popularization of the suicide bomber from the terrorism in the Middle East or wherever else, it became more. We've always had nuclear. We had suicide bomb type people, but it's been a lot more popularized these days due to that terrorism. So we now know we have a lot of people who are willing to die in order for their cause or for their religion. And so now we have to actually worry about the nuclear waste. Sure, it'll kill whoever tries to take it, at least in a day or two. But hey, there are people who are willing to die. So they'll steal it. These people, they'll die. They'll transport it to wherever criminal elements want to use it. So we should be worried about these generally unguarded nuclear waste. Another place we can steal it from, or maybe even buy it from, I don't even know, is actually the former Soviet Union. They stockpiled a lot of nuclear weapons during the Cold War, for whatever reason, and now they don't need it anymore. They don't want to take care of it, so they are not all that, scrupulous about keeping it and keeping it safe and keeping it from being stolen. People can steal it. There are people who can buy it or bribe people to get these bombs. And there are actually reports. They don't want the public to know about this because it gets everyone nervous of this actually happening. And then we actually